Welcome to my talk on Gaussian processes. My name is Vinesh Maguire-Rajpaul. This is me, and I'm a research fellow at the University of Cambridge. My research involves trying to come up with better ways to discover and characterize exoplanets using radial velocity data, and this work often involves Gaussian processes. In this talk, I hope to achieve three main goals. First, I'd like to give you a sense of what a Gaussian process, or GP, actually is. I hope to convince you that GPs are not at all scary and in fact are really easy to use and understand. Second, I'd like to show you that GPs are extremely powerful in general, but particularly in the context of exoplanets and radial velocities, seeing as that's the focus of this year's Sagan workshop. And finally, I'd like to balance out my positive sales pitch with some words on the limitations of GPs. Before we start though, one or two prerequisites. To understand what a GP is, it really is important that you know what a Gaussian or normal distribution is, what it looks like, what the mean and variance are, etc. You should also understand a few basics about multivariate Gaussians, i.e. normal distributions over more than one variable. For example, you should know that they're specified by a mean vector and a covariance matrix, which generalize the mean and variance from the 1D case. If this is unfamiliar to you, a quick skim of Wikipedia or watching a relevant YouTube video would be useful. The other thing you should ideally be somewhat familiar with is Bayesian inference. It would be helpful if you have an idea what prior, likelihood and posterior distributions are and the roles they play when we're modeling data to learn about the real world. If you need to brush up on some basics, I'd recommend reading the first few pages of this short primer, which you can find on AstroPH. Okay, let's talk first about exoplanets and the RV method, because this will motivate the GP stuff we're going to consider later on. You probably know that after transit photometry, the RV method has led to more exoplanet discoveries than all other detection methods combined. Besides that, the RV method is really important for giving us the masses of transiting exoplanets. So this plot visualizes some 600 RV discoveries over the past few decades. Now, for quite a long time, continual improvement was the norm, and the RV method yielded lower and lower mass exoplanets associated with smaller and smaller RV signals. But then, at about the 1 meter per second mark, things stagnated. Instead of being down here, we got stuck up here, which is weird because today's state-of-the-art spectrographs should be sensitive to signals almost as small as 10 centimeters per second, which is about the size of the RV motion that Earth induces in the Sun. So what's up? The short answer is that stars are not just sitting there, waiting patiently for us to observe the subtle RV dances they're performing in response to one or more orbiting exoplanets. Instead, they're hurtling through the galaxy, rotating, pulsating, violently ejecting plasma into space, and more. And all of these things can and do give rise to apparent RV variability that has nothing to do with planets. So stars are, to say the least, active. And this is the biggest barrier we need to overcome before we can discover true Earth-like exoplanets. This, by the way, is an image from NASA's Solar Dynamics Observatory showing a particularly impressive coronal mass ejection. There'll be other talks in the workshop dedicated specifically to this topic, so I'll just say that processes intrinsic to stars do cause apparent RV variability, and this variability occurs on a wide range of timescales. On very short timescales, minutes to hours, we have variability associated mainly with stellar oscillation and granulation. Fortunately, that's not too hard to deal with, partly because most exoplanets we're interested in have much longer periods. However, on longer timescales, from days to months, we start to find stellar signals caused by active regions, so called because they correspond to regions of unusually strong magnetic activity. And these signals are characterized by periods tied to the rotation period of the star. So, for example, these signals could be caused by active regions like dark spots or bright plage and faculae, which will move in and out of view as the star rotates. You might have additional variability on timescales as long as several years for stars that exhibit long-term magnetic cycles similar to the Sun's. In any case, it's these rotationally modulated activity signals that usually cause planet hunters the most nightmares, because they can completely drown out, or even worse, mimic the RV signals of genuine exoplanets. Here, for example, is an RV time series from a star called Kepler-78. You can see that the star exhibits variability that's clearly periodic, repeating every 12 or so days, and with a healthy semi-amplitude of around 20 meters per second. You might think that this is due to a planet or two, but in fact the signal is just due to active regions on the star itself. As it happens, there is also a planet here, Kepler-78b, but its RV signal corresponds to these short period bumps and wiggles, with a semi-amplitude about 10 times smaller than the activity signal. This isn't even a particularly difficult case, but it does serve to illustrate that you really need to model both stellar variability and planetary signals if you want to find the smallest exoplanets. Okay, so to illustrate this, here's a movie of some star spots, some sunspots, as observed by the Solar Dynamics Observatory. Some things to note are, firstly, that the Sun is rotating, as all stars do, and there are a few dark spots visible. These spots have finite lifetimes, so they appear, they grow, they stick around for a while, and then eventually they disappear again. On the Sun, at least, we can identify individual spots in other active regions and study them in great detail, but on distant stars that's usually impossible, so we have to come up with other ways to model their signals that contaminate our RVs. It might not be obvious why rotating active regions give rise to RV signals. To get some insight, you need to consider that when we observe a rotating star, provided we're not looking at it pole on, half the disk will be rotating towards our line of sight and half will be rotating away from us. Therefore, one half will be blue shifted and one half red shifted. But since the star is an unresolved point source, the two effects cancel each other out, and you end up with zero net RV shift. However, as soon as you add a dark spot, say, the flux balance between the two halves will be broken. So at the instant pictured here, there'll be a bit less flux from the red shifted part of the disk, so when we measure the stellar RV, we'll get a net blue shift. And then the star rotates, and sometime later the spot will end up on the other half of the disk, by which point the opposite effect happens and you get a net redshift. And then the spot will be here, so you'll have zero effect, then a net blue shift again, etc. The upshot is that this rotating spot will cause us to measure periodic but spurious velocity shifts. Okay, now if we want to model these stellar activity signals, what do we actually know about them? What are their properties? First, we do know something about their characteristic timescales, which usually range from days to months, depending on how fast a star is rotating. And then on top of that, we might also have long-term magnetic cycles that would last years. Fine. We also know that their signals should be sort of periodic. They might be truly periodic if the active regions never changed. But as we saw in the movie, active regions appear, evolve, decay, so their overall signals will vary over time. There'll still be some underlying periodicity, but the shapes of the signals will change over time. Next, we expect their signals to be somewhat smooth. You won't see sharp discontinuities because the active regions don't just appear or disappear instantaneously, they evolve gradually. And lastly, we could say that the signals will have a stochastic or random component because we have no real way of knowing or predicting when a given active region might appear. Okay, so we're not totally clueless, but at first sight these aren't particularly promising ingredients for building a model to describe and fit stellar activity signals. You're certainly not going to expect a y equals sine of x type effort to capture all this behavior adequately. So how do we build all of this somewhat vague information into a Goldilocks model that is neither too simplistic nor is an unrealistically flexible black box? And I'd like you to hold that thought, hold that challenge in your mind for several minutes, because in order to address it, we're going to turn at last to the main question we need to answer, which is, what is a Gaussian process? And related to that, why should you care about them? Now, when I want to learn something new, I often start with Wikipedia. In the case of GPs, however, I'd suggest that this is not the best place to start. You'll find some mathsy definitions, sure, but you probably won't end up with much real intuition for what a GP is. So you might instead open up this book by Rasmussen and Williams, which you heard was the Bible for Gaussian processes. Even the first pages, though, look a bit intimidating, so you skip further ahead to see if things get better, and instead they look like this. And soon you're vowing never ever to touch GPs again, as you start to deal with a full-blown existential crisis. You know, why is this stuff so hard? Have I picked the wrong career? Is there more to life than this? Maybe that was just me as a PhD student. Anyway, this is actually a great reference, but it's probably not ideal when you're just dipping your toes in the water. So let's introduce GPs another way. We're going to start with a Gaussian distribution over just two random variables, x1 and x2. In this example, the mean of each variable is 0, their variance is 1, and there is 0 covariance between them, i.e. they are uncorrelated. The dots represent different samples from this 2D Gaussian distribution, and the different colors don't mean anything, they're just there to make things prettier. So here, for example, is one sample from the distribution, the green dot, where x1 is about -2 and x2 is about 4. But most of the samples cluster here around the origin. And if I project this 2D distribution onto either axis to get marginal distributions, I get these dotted lines, which are just 1D Gaussians. Okay, so far nothing new. Now, let's represent the same distribution in a new way. We're going to plot all the x1 samples here and all the x2 samples here, with the value of each plotted on this vertical axis. And if we like, we could draw lines between the x1 and x2 samples, just to make it clearer which 2 points are connected in any one sample. So here, for example, is our green point from before, where x2 is about 4 and x1 is about -2. Okay, now here's another 2D Gaussian distribution, but this time with x1 and x2 positively correlated. Here's the old representation, and here's the new representation. You might imagine x1 and x2 are, say, planet masses and radii, which you'd expect to be positively, but not perfectly correlated. In the new representation, you can read this correlation or covariance off by noting that the lines connecting x1 and x2 are often close to horizontal rather than random. And that's because high values of x1 are associated with high values of x2, while low values of x1 are associated with low values of x2. Okay, here's a third example, but this time with anti-correlation. The old representation is easy to interpret, big x1 associated with small x2 and vice versa. In the new representation, this relationship is evident by the fact that you have lots of lines going from high to low, or vice versa, since big values of x1 connect to small values of x2, and vice versa. Right, now we return to the case we started with, and you might ask, why are we bothering with this new representation? The reason is that the representation on the left is fine when we have just 2 dimensions, but it becomes difficult in 3 and useless in higher dimensions, whereas this thing on the right we can use in any number of dimensions. Okay, so let's proceed and increase the number of dimensions. Just to be absolutely clear, as we're moving forward, I'm going to make a note up here of whether we have any covariance between our random variables. For now it's 0, k is just shorthand for covariance. Okay, now let's go to 3 dimensions. Here's x1, x2, and x3. We're still looking at the case where all of our random variables are uncorrelated with each other. So these lines just crisscross all over the plot, up and down, at random. And remember, a single sample from this distribution must now be 3 numbers corresponding to x1, x2, and x3. Okay, now let's kick things up several gears and jump to 100 dimensions, why not? Every sample from our really big Gaussian is now a 100 element vector, which is basically a big array of white noise by definition, since we're still specifying that every random variable is uncorrelated with every other random variable. In technical terms, we're saying that all off-diagonal terms of our covariance matrix must be 0. Okay, now we get to the really important step where you really have to pay attention and hold on to your hats, etc., because this is where the magic is going to happen. What we're going to do is stop saying that all random variables have 0 covariance. Instead, we're going to impose some covariance on our random variables, let's say with this particular form. So if you look at this for a while, you'll see that what we're saying is that random variables with indexes that are close together, say x1 and x2, or x57 and x55, should have a positive covariance, i.e. these random variables should have similar values, but variables with indexes far apart should become uncorrelated. We're still working with a 100-dimensional Gaussian. The only difference is our covariance matrix is no longer diagonal. We now have off-diagonal terms that encode non-zero covariances between variables according to this formula. So let's roll the dice and generate a few samples from this distribution and see what we get. Lo and behold, here are 10 samples, and suddenly we're no longer dealing with white noise. These samples have structure. They almost look like functions. They're not, because each sample is just 100 discrete points, and I'm just drawing these lines through the points to aid your eye. But the samples sort of look like functions, almost. Now, the logical next step, if you're mathematically minded, would be to let the number of dimensions go to infinity and replace the index random variables x1, x2, etc. with a continuum of real numbers. We'll use the same covariance prescription as before. These are just going to be real numbers now. And let's generate a few samples from this infinite dimensional Gaussian distribution. What do we get? Continuous functions. Because after all, you can think of a continuum of real numbers as an infinitely long vector. So instead of generating random vectors, we're now generating random functions. You might need to stop and think about this for a while, maybe pause and rewind the video, because this is a pretty difficult concept to wrap your head around the first time you encounter it. It turns out that the properties of our random functions are determined directly by this recipe we use to specify the covariance between any two different points, this is called the covariance kernel function, hence the k. You pick any 2 points and this covariance kernel will tell you the covariance between random functions at those points. Okay, so let's change the kernel. Let's stick a big number in front of it, and let's insert a 2 inside the exponential so that covariances decay twice as quickly between different points in the function. Now we get random functions that look similar to before, but we see that the output scales or amplitudes are about 100 times bigger, and the input or length scales are twice as short, which is what we may have expected since covariances decay twice as fast, allowing nearby points to have more dissimilar values. So before and after. I should probably emphasize that it's not the shape of these functions, not the shapes of these functions that are Gaussian. After all, these functions look absolutely nothing like Gaussians. Rather, it's the specific way our knowledge or uncertainty of function values at one point influences function values at other points that is Gaussian. This is the Gaussian bit. So that's a bit abstract. But crudely, you could think that it's the uncertainty in our functions that is Gaussian, not the shape of the actual functions. In fact, depending on which covariance kernel we choose, the functions could have literally any shape at all. Okay, one more example. Instead of squaring the term inside the exponential, we'll just take the absolute value, meaning covariances decay in a different and slower way with distance. What do we get? Again, random functions, though this time with quite different properties. Now they're jagged rather than smooth, yet they're not uncorrelated or white noise. They do still have some structure, and a given point in any function will on average still be more similar to nearby points than very distant points. It turns out that functions generated with a kernel like this one correspond to Brownian motion, or you might try to use these functions to describe some fairly haphazard process like price movements on a stock market. Anyway, such details aren't important. What is important is that we can, at last, characterize a Gaussian process as follows. A GP is just the infinite dimensional version of our old friend, the multivariate Gaussian distribution. So, a 1D Gaussian is specified by a mean and a variance, which are just two scalars, and samples from the distribution will also be scalars. An ND Gaussian, multivariate Gaussian, is specified by an n-element mean vector and an n by n covariance matrix, which defines the covariance between all pairs of random variables, and samples from the distribution in this case will be vectors. Finally, a Gaussian process is specified by an infinitely long vector and a mean vector and an infinity by infinity covariance matrix. But of course infinity is far too big, so instead of specifying infinitely many values, we content ourselves with a mean function and a covariance function that provide recipes for computing any values we're interested in. Importantly, samples from a GP will be entire functions. In other words, GPs give us a way to formulate probability distributions over functions. Okay, now you might well say, if GPs are infinite dimensional objects, how can we actually work with them in practice? It turns out that the remarkable properties of Gaussian distributions allow us to integrate out all of the infinitely many values we're not interested in, so that we can evaluate marginal and conditional distributions analytically for any finite number of values we are interested in. It also turns out, thanks to something called the conjugate property of Gaussians, that if you use a GP as a prior distribution over functions and combine that with some data and a Gaussian likelihood, you'll end up with a posterior distribution that is also a GP. Now, those 2 points are rather technical, so let me try to put things in simpler terms. If you assume you have some data that can be described by an unknown function, and you use a GP as a prior over possible functions, you'll end up with a posterior distribution that is also a GP and that you can evaluate analytically. In even simpler terms, we can use GPs to learn unknown functions plus error bars on the function directly from data. Best of all, we can reuse all the familiar machinery of inference that we already use for parametric functions like y equals mx plus c. That's pretty amazing. Instead of learning the parameters of a single known function, we can learn unknown functions from data. Now, what does regression or fitting with a GP actually look like? Let's say we have a series of observations, yi at times ti, plus some Gaussian noise, and we assume that these observations can be described by an unknown function, f. So we place a GP prior over f, and this GP is fully specified by a mean and a covariance. The mean function is uninteresting, and we usually just take all the deterministic stuff we already know how to parameterize, for example, signals due to planets, and cram those into the mean function, which will then depend on some parameters. Or sometimes for simplicity, people just set the mean function to 0. The covariance, on the other hand, is the beating heart of any GP regression, and this controls the properties of the unknown functions we want to model. This would usually be stochastic signals and or anything we don't know how to parameterize, for example, stellar activity. The covariance will usually depend on a small number of so-called hyperparameters which control the properties of the functions that we can describe. Now, once you've specified your mean and covariance functions, it turns out you can write down this very straightforward log likelihood for your data, given parameter and hyperparameter values. In fact, you may recognize this as being identical to the log likelihood you'd use whenever you're doing regression with uncorrelated Gaussian noise. The only difference is that K is no longer a diagonal matrix. So it's really remarkable that the log likelihood turns out to be a familiar finite dimensional thing you can compute with some linear algebra, even though GPs are formally infinite dimensional distributions. Fitting a GP to data now simply entails finding the values of these parameters and hyperparameters, much like finding the values of parameters for ordinary functions, for example finding the slope and intercept in a linear model. Once you've learned the hyperparameter values and you want to condition your GP on observations to make predictions with error bars, that also turns out to require only basic linear algebra. So what does this look like with actual data? Here are some noisy observations I synthesized using a fairly complicated parametric function, the details of which we assume have been lost forever. Instead, all we know is that the function has some sort of periodic behavior. So I start with a GP prior with an appropriate covariance kernel, go through the maths on the previous page, and presto, I end up with a posterior prediction, that's the blue line, for the unknown function that looks remarkably similar to the true function, the red line, that I used to generate this data. Better still, I have error bars, which correspond to plus minus 1 sigma coverage of the infinitely many functions that are compatible both with my data and my prior. Now I can interpolate and extrapolate, and as you can see, my uncertainty gets bigger as I get further away from the data. Okay, so we know that the covariance function is the most important part of any GP. But what sort of function properties can you actually encode via covariances? Properties you can specify include how smooth or jagged functions are, input scales, i.e. how fast functions change over time, or space or any other input, output scales, i.e. the amplitude of functions, which may also include noise amplitudes, strict periodicities or quasi-periodicities, stationarity, which relates to things like long-term trends or sudden change points, isotropy, etc. Now this does require a different way of thinking compared to when you parameterize functions directly. But then a little reflection will reveal that many of these properties are exactly the sort of somewhat vague bits of knowledge we do have about stellar activity signals. For example, the smooth growth and decay of spots will give rise to smooth functions. Spot evolution times or lifetimes will determine the timescales of activity signals. The fraction of a star's surface covered in spots will influence the amplitude of activity signals. Stellar rotation combined with spot evolution will give rise to quasi-periodicities, and long-term magnetic cycles could lead to long-term RV trends. In other words, we can use physics to inform our choice of covariance function, and we'll be able to get physical information back out of the hyperparameters we end up fitting. To illustrate this, let's consider the following widely used covariance kernel, often called the quasi-periodic kernel. There are just three main hyperparameters. The first is a characteristic or overall period. The second controls how much structure functions exhibit within a single period. And the third sits inside this exponential decay envelope and governs how quickly functions evolve or decay away from strict periodicity. By varying these three hyperparameters, we're able to model an enormous diversity of periodic and quasi-periodic functions, a few examples of which I've plotted here. In the top row, we have functions with shorter periods, and in the bottom row, longer periods. In the left half, these four panels, we have relatively simple periodic functions, And then in these 4 panels, we have more complex functions, showing more structure or bumps and wiggles per period. Finally, we have some functions here and here that evolve or change shape very quickly, while the functions here and here change shape slowly and are closer to being strictly periodic. There's a lot to look at here, so you might want to pause the video for a few moments. And I should add that the amplitude of the functions would usually be controlled by a 4th hyperparameter, but I've left that off because it's pretty boring. Okay, so now you might ask, why go to all this trouble? Why not just make a conventional parametric model for stellar activity? It turns out that doing so is extremely difficult. Here's an example of a model that was used in a well-known study to try to describe the activity variability of Alpha Centauri b, which is the 2nd closest star to the Sun after Proxima Centauri. To account for quasi-periodic and non-sinusoidal variation and activity cycle changes across 4 observing seasons, the authors here devise a model with 23 free parameters just for stellar activity, without any planets. So you can ask several questions. Okay, maybe this model does a decent job of fitting the data, but why this model? What physics does it encode? How do you interpret and constrain all these 23 parameters? Why don't you use a model with 15 or 22 or 35 free parameters? And if you did so, would you end up with different conclusions about any planets that might be present? This study was done before GPs had really arrived on the RV scene. If we were doing the same thing now, we'd probably turn to our quasi-periodic covariance kernel from the previous slide, this fellow, which has just 3 or 4 hyperparameters, all amenable to physically motivated priors. Remarkably, the simple-looking covariance kernel can reproduce the complicated model on the previous slide as a special case. However, when we work with a GP model like this, what we're really doing is acknowledging that we don't know what the correct parametric description for our data is. And so we explicitly build that uncertainty into our model, and we actually work with a distribution, that's the GP, distribution over infinitely many possible functions, instead of working with just one, almost certainly incorrect function. Okay, before we discuss some applications of GPs, I'd like to emphasize that writing your own GP code completely from scratch is really easy. You'll learn literally 1,000 times more if you actually do this yourself, make some mistakes, play around, than if you just install someone else's code and never figure out the basics. On the left, for example, I wrote some simple Python code that sets up a quasi-periodic covariance kernel, draws samples from the kernel, and computes log likelihoods. I don't claim this code is efficient, but it works. The next steps, conditioning on data and making predictions, are also really easy to code. Once you get a feel for the basics, there are of course many existing and powerful packages in Python you can turn to, some of which I've listed here. The first one, gpy, is particularly good for beginners, while the others might be more suited to advanced applications with big data. Right, now we're ready to consider some exoplanet-related applications of GPs. I won't go into very much detail, but I hope I'll be able to give you some sense of how versatile and powerful GPs are. In general, when we make astrophysical observations, there'll be one or more signals we're actually interested in, say planets buried in RV data. Side by side with this, there'll be variability due to nuisance signals, also known as correlated noise, that we're not interested in, but it's there anyway. Finally, we'll have uncorrelated noise, for example photon noise, and all these things combined will give us our observed data with formal error bars that almost always only encapsulate the uncorrelated stuff like photon noise. So we learn how to deal with the photon noise and the planets or whatever in our undergrad class, but here's the elephant in the room, these correlated nuisance signals, and that's where we leverage GPs to model this messy stuff. For the longest time, people just ignored this or tried to sweep it under the rug. In other words, they assumed that their observations were just signal plus uncorrelated noise. But of course, sweeping an elephant under a rug is never going to work very well, and doing so will likely mess up inference about the signals you're actually interested in. Okay, with that in mind, let's look at our first application. And no prizes for guessing that it's modeling stellar activity signals in RVs. In short, if you model stellar signals in a principled way with a GP, you'll almost always be able to characterize planets more accurately, and more importantly, be less likely to mistake stellar signals for planets compared to when using cruder or less principled approaches. Two significant early examples of GPs being used in this way are the Corot 7 and Kepler 78 systems. In this plot on the right, you see the observed RV variability of Corot 7, which Hayward et al. Modeled as a GP up here to account for stellar activity, plus 2 planets. And down here are their well-behaved residuals. By taking this approach, they were able to reject a potential third planet that had been suggested by other authors. And this approach usually works extremely well, except when a star's rotation period is similar to a planet's orbital period, and then you can run into problems, because the GP by itself doesn't necessarily know whether it's fitting a star or a planet. So during my PhD, my supervisor and I developed a framework to address this problem. We assume that there's some physical process responsible for activity that we don't observe, but that we can model with a GP. We then figure out how this process, this GP, will propagate into different observables, RVs being one of them, but also other time series that are sensitive to activity but not planets. For example, the spectroscopic activity indicators. We do allow planets to contribute signals to the RVs, but not the other time series. So when you put all this together, you end up with GP regression over multiple inputs and outputs simultaneously, instead of only RVs. The maths is a bit more complicated, but it works well even when stellar rotation periods overlap with planet orbital periods, and it's been used to discover or characterize several planetary systems. If you're interested in learning more, here's the paper presenting the framework, and here's one recent application paper. The next application is closely related to the first, and that is studying periodic phenomena, including, for example, stellar rotation. Almost every astronomer knows and loves the Lomb-Squargle periodogram, which is fast and easy to compute and understand. It's perfect for characterizing periodicity if your data consist of a single sine wave plus white noise. But as soon as that assumption is violated, you risk being led astray. What happens when you have multiple non-sinusoidal quasi-periodic signals corrupted by correlated noise? Well, easy. Just replace your naive sinusoidal model with a more appropriate GP model, say using our old friend, the quasi-periodic kernel. If your main interest is periodicity, you can marginalize or integrate out these other hyperparameters and make a sort of GP periodogram. So here, for example, are some noisy and gappy data I synthesized that are meant to represent the photometric signal of evolving active regions on a rotating star, with a period of about 38 days, I think. If you look at the Lomb-Squargle periodogram in red, it's noisy, multimodal, and the highest peak doesn't even correspond to the true rotation period. And the simple reason is that we're implicitly fitting the wrong parametric model to the data. The posterior distribution for the GP period, on the other hand, does peak very close to the true period. I repeated this for a few hundred such simulations and found that the GP error in the inferred period was about an order of magnitude smaller than that provided by the Lomb-Squargle analysis. Not surprising, because it's a more appropriate tool for the job. And if you'd like to learn more, you could have a look at this paper by Angus et al., which features a bunch of tests which are similar to, though more sophisticated than, the simplistic ones I just showed you. Now, a rather different application of GPs comes in the form of modeling stellar spectra themselves, i.e. the very things we use to infer RVs in the first place. Often this takes a lot of work and specialist knowledge of stellar astrophysics, chemistry, atmospheric physics, etc. Even just to build template spectra. But with GPs we can build a very good non-parametric model for spectra with almost zero effort. Here, for example, is part of one Eshel order in a Harps North G-dwarf spectrum, and down below a zoom in on an even smaller wavelength range. Superficially, at least, the GP seems to provide a great model. Of course, you do lose quite a bit of physics in the process, but if all you need is to extract RVs, which basically means aligning lots of spectra, that doesn't really matter. And using GPs in this way actually gives you a simple and quite robust route to extracting RVs. If you're interested in learning more, I refer you to these two papers. And I should add that if you're clever about how you extract RVs with some of these techniques, you can also reduce the stellar activity contamination so significantly that you don't even need to model it in the RVs you extract. But that's work in progress. Right, application number 4. Turns out that the instruments we use to observe things are not always well behaved. An excellent case in point is the Kepler spacecraft during the K2 mission, by which point 2 of Kepler's reaction wheels had failed, and light curves were affected by severe and very complex systematics. Complex, but with some structure, which made them amenable for modeling with a GP. So that's exactly what Agram et al. Did. They developed a pipeline, K2SC, that corrects Kepler's instrumental systematics simultaneously with stellar variability in light curves. So in this plot you see raw K2 flux up here, flux corrected for instrumental systematics only, flux corrected for stellar variability only, and the residuals from the full model that corrects both components. Clearly it works pretty well. If you're interested in more details, here's the reference to the K2SC pipeline paper, and here's a slightly older paper that uses GPs to model instrumental systematics in the context of transmission spectroscopy. Admittedly, this isn't RVs, but there's no reason that GPs couldn't be used to deal with instrumental systematics in an RV context. Then a final application which is really simple, though maybe underappreciated, that is using GPs as a simulation tool. What you can do is train a GP on real data with all its awful complexities, noise, patchy sampling, stellar and instrumental nuisance signals that you probably don't even understand, etc. Once you've done that, you immediately have a tool for generating unlimited amounts of synthetic data with covariance properties that match your real data. This could be useful, say, if you needed realistic data for studying optimal observing strategies or detection limits. It can also be useful for identifying artifacts associated with fitted models or discrete sampling, by which I mean that if your model finds a planet in synthetic data that you know doesn't contain a planet, then you've got a problem. One notable application of GPs in this way was showing that Alpha Centauri BB, for a while thought to be the closest exoplanet to Earth, was most likely a false positive related to gaps in the data and a suboptimal activity model. Specifically, in fact, the big 23 parameter model I showed you earlier. If you'd like to know more, you can have a look at this short paper. Okay, so much for the applications. Now, the original title I was given for this talk was The Power and Dangers of GPs. And I don't think GPs should be considered dangerous any more than sine waves or calculus might be considered dangerous. And using this term might reinforce an idea of GPs, some sort of evil sorcery or black magic that you'd only turn to in desperation, which really isn't the case. So I'll talk instead about the limitations of GPs. The first and most well-known limitation is that GPs can be really computationally expensive. Regression with GPs requires inverting a covariance matrix many times. Matrix inversion is really expensive and scales like n cubed for n data points. Basically, GP regression is fine up to about 1,000 data points, but then n cubed becomes ridiculously big. Oops, sorry. For RVs, this isn't really a problem when even a few hundred observations would be plenty, but for space-based photometry, this is a real issue. Fortunately, there are clever techniques that can make GPs work even on much larger datasets, at least in some special cases. I'd refer you, for example, to the Python packages George and Celerity by Dan Foreman-Mackey et al., and also GPFlow and gPyTorch, not by the same people, I don't think. The second potential limitation is that pretty much everything with GPs hinges on the covariance kernel. In the stellar activity example, we do have a physically motivated kernel at our disposal, but that's not always the case, and if you choose an inappropriate kernel, you might get superficially good but actually nonsensical results. Garbage in, garbage out, basically. Designing or choosing appropriate kernels is a big topic in itself, but just to give you an example of some of the subtleties, consider the quasi-periodic kernel we've seen a few times now. If we allow the functions to evolve on timescales shorter than a single period, p, then functions at time t won't even look similar to the same functions at time t plus p, and so the very idea of periodicity becomes meaningless, which would be bad if you're trying to characterize periodicity, so you have to be careful. Compounding these issues, the hyperparameter posteriors can be multimodal and degenerate. Here, for example, are some quasi-periodic data that we can fit with a period of 25 days and low harmonic complexity. We can fit the same data almost equally well with a period of 100 days, but higher harmonic complexity, i.e. more structure per period. So in practice, what this means is you need reasonable priors for your hyperparameters, and you really need to explore their posteriors thoroughly and simultaneously with other parameters in your physical model, for example planet parameters, instead of taking lazy shortcuts like trying to do max likelihood optimization, which could lead you astray. A third issue is that if you're not careful, a GP might eat your planets, so to speak. This is something that people do worry about, especially those who are skeptical of GPs. It is actually quite hard to overfit with a GP, but that doesn't necessarily stop a GP from fitting the wrong signal, especially if you don't use it properly. There are a few solutions here. As already noted, you should always use sensible priors for your hyperparameters. More importantly, once you fit a GP to your data, you need to compare the Bayesian evidence for the GP model to the evidence for a simpler model. Because if you can fit something with a simple Keplerian, say, instead of a GP, the Bayes factor is probably going to scream this fact at you. This is a really important modeling step that people often overlook. A complementary solution we saw earlier would be to use as much available information as possible, apart from just RVs, to constrain the GP. And finally, worrying that a GP will eat your planet is a valid concern, but there's an equally important danger, which is the converse of this. Namely that if you don't model nuisance signals properly, say with a GP, you could conclude that you have more planets than are really there, or you could infer completely incorrect parameters for genuine problems. My collaborator, Eva Maria Ara, should have a poster at the workshop showing exactly this problem on some real data. Now, a final limitation is encapsulated by this picture, where someone is trying to hammer a screw into some wood and use a spanner to do who knows what with a nail. These are both probably perfectly good tools, but they're clearly the wrong tools for the job. And if you try to work in this way and got bad results, you might well be tempted to blame the tools. This applies also to GPs, which are powerful, but not always the right tool for the job. For example, if you know how to parameterize the physics you're modeling, maybe you're looking at a simple harmonic oscillator, or to take more complex versions of related phenomena, maybe stellar acoustic oscillations or cosmic microwave background temperature fluctuations, whatever. You don't need a GP. Your life will be simpler and you'll get better results if you just use the parametric model. Another case where GPs might be inappropriate is when your noise is non-Gaussian. For example, if you have many outliers or some heavy-tailed noise process at work. There are ways to deal with such situations, but fortunately the central limit theorem reassures us that in practice our noise will very often be close to Gaussian, in which case GPs are just fine. Okay, so by now your brain probably feels like this, so this would be a good point for us to make a quick summary of what we've learned and wrap things up. First, how did we characterize a GP? We said that GPs are the infinite dimensional version of the Gaussian distribution. This is useful because GPs define distributions over functions, and it turns out that we can use this to learn unknown functions with error bars directly from our data. All we need is to pick a covariance kernel that reflects whatever prior knowledge we have, and then a little bit of linear algebra will make all the magic happen. Right, well, why are GPs great? We've just said that they enable data-driven Bayesian inference about functions, which is pretty remarkable. They're extremely flexible and powerful, as I hope the applications I showed you suggested. And despite this, they're really not black boxes. You can usually constrain and interpret their properties using actual physics. They're probabilistic, which we could encapsulate by saying they know what they don't know, which is certainly not the case for many machine learning techniques, including neural networks. They're really easy to implement, and finally, they're often a lot better than the alternatives, especially when one of those alternatives is ignoring correlated nuisance signals completely or trying to account for it with hopelessly inadequate parametric models. But that's not the whole story. We also heard about some of their limitations. They can be computationally expensive. Choosing a good covariance function is critical, and you have to be quite careful interpreting and constraining the hyperparameters. It's also essential that you sample their posterior distributions really thoroughly. GPs, being flexible as they are, can fit just about anything if you misuse them, so don't do that. And finally, great as they are, they're not always going to be the right tool for every job. If somehow you've survived this far into the talk and have decided you might actually want to learn more about GPs, here are two suggestions. First would be this short tutorial by Steve Roberts et al., which is probably my favorite introduction to the subject. It's short and intuitive, but also provides enough mathsy detail for you to code up all the essentials. The second reference I would suggest would be this thesis by some completely random person, not because said person wants to engage in shameless self-promotion, but because as a reference this does at least introduce GPs and develop GP applications, specifically in the RV context. And so it does provide a lot more detail on many of the things you saw in this presentation. Okay, so I'll end there. I hope you found this somewhat useful, and if you do have any questions or comments, please feel free to drop me a message. Thanks.